Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on torque slip characteristics of three-phase induction motor. So first, what do you mean by slip and torque? First, torque definition. Torque and next slip definition. The slip definition means here torque definition, turning moment, that means twisting force in which the force turning moment in which tends to cause rotation about axis is known as torque. Torque units are Newton meter. Now here slip. How what do you mean by slip? So before going to define the slip, I have one question. What will happen if rotor reaches the speed of the stator flux? If rotor reaches the speed of the stator flux. Speed of the stator flux means that is RMF speed. So now here what will happen? There is no relative motion between stator field and rotor conductor. If rotor speed is NR and this is the NS, and if it is reaches this one, so there is no relation motion between stator field and rotor field. So there is no relative motion between these two, means dynamically induced EMF. Their E is directly proportional to the d phi by dt. If there is no relation motion, means there is no induced EMF. There is no induced EMF means rotor bars are short circuited, so there is no induced current. Means no torque. No torque will be generated. There is no mechanical power. Motor will not rotate at the shaft. If rotor reaches the synchronous speed, Ns equals to 120 F by P, and here Nr equals to Ns, it will not rotate. Now here, is it possible? Is it practically possible? Second question. So no, it is not possible. It is not equals to Ns equals to Nr because the friction. So because of the friction, so rotor will slow down the rotor. Next, hence the rotor speed is always less than stator speed. This is the Ns, stator field winding speed, and this one is the NR. This NR is always Ns. This is the asynchronous machine, and the difference is known as the slip. Ns minus NR is this. NR is known as the slip. This is the slip, and slip equals to percentage slip equals to the difference in the rotor speed and stator magnetic field, rotating magnetic field, that is Ns synchronous speed divided by synchronous speed, actual speed, and this is the synchronous speed Ns minus actual speed Nr divided by Ns. Now here, if you see here, Ns minus Nr divided by Ns, that equals to 1 minus N by Ns. This is slip. And the slip range. So for satisfactory rotor, the slip must be 1, but in generally this value is from no load to the full load. This value is 0.1 to 0.01 to 0.1. The speed of the motor is always constant. Now slip indicates the difference in the rotor speed and rotating magnetic field, Ns. Now here the difference in the speed is expressed as a ratio is known as the per unit slip. This is per unit slip. Percentage slip means that is into 100. So synchronous speed Ns minus Nr divided by Ns is a per unit slip, and percentage slip equals to Ns minus Nr divided by Ns into 100. This is the percentage slip, and this one, if it is not 100, that is per unit slip. So for most of the machine, slip varies from 0 on the, for no load this value is around 0.01, and When it is full load, that value is 0.1. So it is depending upon that friction over friction at the bearings. And now here this is most important, slip value is 0 and slip value is 1. Now we know this ns equals to 120 f by p, and here s equals to ns minus nr divided by ns. So now if motor runs at synchronous speed, so now motor runs at synchronous speed means ns minus n or nr value is nr equals to ns means this is ns. So ns minus ns means this value is 0. If motor runs at synchronous speed, that slip value is 0. This is most important. And next case, if rotor is stationary, rotor is at initial position. So now s equals to ns minus ns. This is n minus nr. This is at rest position, at stationary, and at that case this nr equals to 0, and this the speed of the rotor is 0, ns by ns, that equals to 1. The slip value is 1. Now this slip value is always between 0 to 1 in case of induction motor, and if it is greater than 1, if it is less than 1, that I will explain in the torque slip characteristic, that induction generator braking condition. Now this from no load to the full load, this value range is 0.012 and 0.1. This is for full load and this is for no load. Full load and no load. At synchronous speed this value is 0, and at rest position this value is 1, slip value. Now what is the relation between torque slip characteristics? Torque and slip. Torque and slip, what is the relation in induction motor? If you know the relation, then you can draw the torque slip characteristics for induction motor. So first torque equation in terms of slip, so that you need to derive. Torque is depending on both the fields means rotating magnetic field and rotor flux, and the phase relation between them. So now phase relationship between them means here rotor current, and this phi is the stator flux, and phi 2 is the power factor of the rotor circuit. Now here T is directly proportional to the phi, and T is directly proportional to the I2, and T is directly proportional to the cos phi 2. Here phi is the stator flux per pole, phi, and next phi 2 E2 I2 is the rotor current, and phi 2 is the power factor of the rotor circuit power factor. Now here phi is directly proportional to this phi is directly proportional to the E. So this phi is directly proportional to the E means you can substitute this final. So phi I2, T is directly proportional to the phi I2 and cos phi 2. Now here T is directly proportional to this phi is directly proportional to the E means rotor EMF per phase at standstill condition is directly proportional to the phi. Now at that case this is phi indicate this is E, I2 and cos phi 2. So this is the equation. Now T equals to K into I2 into E2 into cos phi 2. Now torque is depending on I2, rotor current, rotor induced EMF, E2 and rotor power factor. So this one, rotor current, rotor induced EMF, rotor current and rotor power factor. This is the torque. So the torque, and how it is depending on slip. So now here rotor current and rotor power factor, and next here rotor resistance. So what do you mean by rotor current? I2 formula and cos phi 2 formula and E2 formula. So if you know this, you can derive the torque equation. First I2, so rotor current, this is the I2, and rotor power factor, this is the cos phi 2. Now here R2 is the rotor resistance of rotor, having some resistance and reactance, rotor resistance per phase of the rotor, that is R2, and next rotor reactance, that is reactance per phase of the rotor, that is rotor reactance formula. If it is having that omega L, that equals 2 pi f L, rotor inductance is L2. Now E2 is the induced EMF per phase of the rotor. According to the Faraday's law of electromagnetic induction, D is directly proportional to d phi by dt, and induced EMF will be developed in the rotor conductor, that is E2 rotor. Here E2 is always represents the rotor. 2 suffix 2 indicates the rotor, and at standstill condition S equals to 1 only. I am representing this. Z2 equals, we know this. If you know the R and X, then you can determine the impedance value. Z equals to R plus JX. So now Z equals to R square plus X square, if you take the magnitude, this formula. And next, rotor current equals to voltage by impedance. So here voltage is E2 and this impedance, and rotor current equals to now E2 by R2 square plus X square, this one. Rotor current equals to E2 by square root of R2 square plus X2 square. Now what about the power factor? Power factor equals to this R2 equals to this I2 equals to E2 divided by R2 square plus X2 square. Now power factor means that is cos phi equals to, from the power triangle, this is R, this is X, and this one is Z. So this is a phi. So here cos phi equals to, from the power triangle, R by Z, this one. So now here, so from this power factor of the rotor circuit, cos phi equals to, this is for rotor, R2, X2 and Z2, and this is the R2 by Z2, this is the cos phi, and R2 is same, and R2 Z means R2 square plus X2 square, this is. Now we have the formulas. First, at slip, in the previous class, this one S equals to 1 only, slip value is 1, and this, in this case also slip value is 1. Now when it is a slip, at slip S condition, the induced EMF S equals to, induced EMF per phase equals to, that is multiplication of S in slip multiplication of rotor, and next reactance equals to 2 pi f L2. So there is a rotor flux, stator flux into stator frequency into S, and that is S, this is the S into S. And now impedance, in the previous case, Z2 equals to square root of R2 square plus X2 square. Now here one extra term S is there here. Now this is a S into X2 square, S square X square. This formula is important. Now impedance per phase, Z2 equals to R2 square plus S into X whole square. Now cos phi equals to R2 by this one, R2 by R2 square plus S X2 square, and I2 case also E2, and E2 means that E2 S into E2 square root of R2 square plus S X2 square, that equals to S into E2 divided by square root of R2 square plus S square X2 square. Now we have cos phi formula, cos phi of 2 formula in terms of slip, and X2 formula, I2 formula, and E2 formula. So now substitute in the one equation. So this one E2 means S into E2, and here this one equals to S into E2 divided by square root of R2 square plus S into X2 square, S square, and next this one equals to R2 divided by square root of R2 square plus S square X2 square. Now here substitute here I2 this one, and cos phi to this one, and this is E2, and this one is I2, this is I2, and this one is cos phi 2. At running condition, cos phi equals to R2 by square root of R2 square plus S x2 square, and I2 equals to rotor current equals to S into E2 divided by square root of R2 square plus S x2 square. And now here, if you multiply this one, K into E2 is square and R2 S divided by R2 square plus S x2 square whole square, and this one. So this is 2 times. So this square and this square root gets cancelled. So the final equation for torque equals to, this is the final formula, T equals to K into S into R2 E2 square divided by R2 square plus S square x2. This is most important. Final equation, torque equals to K into S into R2 E2 square divided by R2 square plus S square x2 square. So now this is, now we have the relation between torque and slip. So we have the relation between torque and slip. So torque and slip. So from this relation we can draw the torque slip characteristics. So first here, so how you will draw the circuit? So torque slip characteristics. So first here, torque slip characteristics can be drawn between torque and slip. This is the slip and this is the torque. Now here torque, this one is torque and this one is the slip. So first case, what will happen when motor is from no load to the full load? So if it is motor, 3-phase induction motor at no load to full load condition, what will happen? Motor is loaded and speed is decreases. When motor is no load to the full load and speed is decreases, and speed decreases means slip increases. Speed decreases and slip increases. Slip increases means to satisfy this load demand, so torque must be increases. Torque must be increases means slip is directly proportional to the S. Now here when speed is synchronous speed, slip value is 0 and torque value is 0. When slip is near to the NS, so slip is low and the characteristics is straight line passing through the origin. If it is directly proportional to the S, means that is straight line passing through the origin. As slip increases, the speed drops with increases in the load and torque increases till R2 by X2 slip value. Now here see this diagram first here. This one. So first slip value is 0 and slip value is 1. When motor is loaded from no load to the full load, speed no load to the full load, speed is decreasing and slip value is increasing. Slip value is increasing and speed value is decreasing. No load to the full load. Now in this case, the torque slip characteristics are straight line passing through the origin, and this is the stable region, OA region. Now next case, until R2 by X2, this is the maximum torque. This one. Now here the maximum value of torque is pull out torque and that is breakdown torque, this value, and further it is increasing slip, so the torque will be decreases. So in this case, so here we have to low slip region and high slip region. in the high slip region, so the torque is inversely proportional to the S. So here, if motor is no load to the full load, the speed is decreasing and slip is increasing. So to satisfy this load demand, torque should be increased, but here the speed is further decreases. So in that case, torque is inversely proportional to the slip. Now here in the inversely proportional means that in that case, that this is up to maximum value. In this case, rectangular hyperbola. Now up to B. This is up to B value. So now this is OA is the stable region and this AB is the unstable region. And here point A is the maximum torque slip value equals to R2 by X2. And at B is the starting torque. This is the starting torque and C is the full load torque. Now, here, torque slip characteristics. Now we have three modes depending upon the slip value. So now if slip value is less than, if it is negative, that is generating mode. If it is 0 to 1, that is motoring mode. Sorry, slip value 0 to 1 and less than 1. And this is the braking mode. Braking mode means here slip value is 0, slip value equals to 0 and slip value equals to 1. This condition. In the previous slide we discussed this one. Slip value is 0 and N equals to NR equals to NS. And the diagram should be like this. And slip value equals to 1, NR equals to 0. Speed value. Now here this case, slip value is 0 and NR equals to NS, and the diagram should be like this. This one. And this is at slip value equals to 1. So this is the starting torque. So now here this is the case for motoring case, slip value from 0 to 1 condition. And next, slip value is greater than 1. So S value is greater than 1. So if it is greater than 1, so now the speed is negative. So the speed is negative means that is in the rotor rotates in reverse direction. So that is motoring braking condition. So motor rotates in reverse direction. In that case, so what will happen? Motor should be rotated means already we discussed. So this is a 3-phase induction motor. So 3-phase supply R, Y, B, and this is the R, Y, B. This is 3-phase balanced supply is given to this one R, Y, B. And rotating magnetic field will be developed and it cuts the rotor conductors according to the Faraday's law of electromagnetic induction, and induced EMF will be developed in the rotor conductors. Rotor conductors are short circuited and currents produces, that currents set up the flux, that flux and this rotating magnetic field and induces the force, that force is mechanical energy. Now here that 2R, if I change these two terminals, by interchanging any two terminals of the stator of the 3-phase winding, so motor rotates in reverse direction. So that is the case, slip is greater than 1. Now at generating stage, generating induction generator, this is induction generator. Induction generator case, so what will happen? So now here slip is negative. Slip is negative means it rotates with above the synchronous speed. So NR is is above the synchronous speed. So NS above the NR is above the synchronous speed. So that is the generating that motor here. So here mechanical energy will be generated, but here electrical energy will be generated. So that is the generating region, motoring region, and braking region. So these are the torque slip characteristics for three-phase induction motor. This is for three-phase induction generator, and this is braking condition. So this is the straight line, and this is the reverse case, negative. Now let us take one. This is now here torque slip characteristics are rectangular hyperbola if this starting resistance is increases. So now this is the maximum torque. So here this resistance is R2 is increases. So diagram should be like this, and motor operates between slip and slip maximum value. If greater value of R, so the greater value of slip at maximum torque occurs. This is at maximum torque. And these are the torque speed characteristics. So reverse case. Now let us take one problem. A 6-pole 50H squirrel cage induction motor runs on no load at shaft speed 970 rpm. Calculate the percentage slip and the frequency of induced current in the rotor is. So that is FR you need to calculate, and this is the percentage slip. So first solution for this. So the given data, NR equals to 970 rpm and number of poles P equals to 6 and F equals to 50 H. And what are the required formulas here? FR equals to S into F. Here F is the supply frequency and S is the slip, and FR is the this one. And percentage slip equals to NS minus NR divided by NS into 100. Now what about NS? Here NS equals to 120 F by P. Here we have 120 F by P. F is 50 and P equals to 6. So 120 F by P, F equals to 50, this one, and number of poles 6. From this you can calculate the squirrel cage induction motor synchronous speed. So that is 1000 rpm. Now here, so synchronous speed is okay. Now this percentage slip, calculate this one. Percentage slip equals to NS minus NR divided by NS. So into 100. So this is percentage slip. So 1000 is calculated from here, minus 970 divided by 1000 into 100. That equals to 1000 minus 30 by 1000 into 100, that equals to 3. Percentage slip is 3% here. Now the frequency of induced current in the rotor circuit is here, this one. So this is the 0.03 and frequency is 50 Hz. So now substitute here. So FR equals to S into F, that equals to 0.03 into 50, that equals to 1.5. So this frequency is always less than the supply frequency. Okay, now this value is 3% and this value is 1.5 Hz. I hope all these concepts are clear to you. If you still have any doubts in this concept, you can comment in the comment section below. I will answer to your queries. Thank you. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.